our numerical, we solve these differential equations, and we find our time scales, but of course it's going to depend on this parameter here. So we need to make an educated guess for this parameter, and we use now we use real values. So we want to model a Milky Way like galaxy. So we use a total initial mass of 10 to the 7 and a semi-major axis 0.5 parsecs, and the inflow rates of course it's not very useful using this, it's just the number of clouds per unit time, so we are using mass inflow, and we have this the inflow of gas to the central parsec, because we are using this A0, so the separation of the binary is more or less 1 parsec, and we use two inflow rates, 1 solar mass per year and 10 solar mass per year. Okay, so this is typical numbers for a post-merger gas-rich Milky Way-like galaxy, inflow of gas to the central parsec. And with this we get a time scale for gravitational waves, which is more or less, of course it's going to depend with the different anisotropies that we use, but it's more or less 1 gigayear for an inflow of 1 solar mass per year, and it's going to be time scale for gravitational waves. It's going to be 0.2 gigayears. Okay, so with this we can say, within of course the limitations of our model, that this process can be efficient to bring these binaries to the gravitational wave regime within a Hubble time. So this is something that is not taken into account yet for any study, that can be a relevant process for the evolution of the binary. So I think that's all that I wanted to say.
So the TGW you have there, that's the time scale until you get to the point
Yes.
where gravitational wave takes place.
Exactly.
But the inflow rates, you just get them, or you took them from
No,
somewhere? You
yes, it's typical values for post-merger gas-rich
Oh,
galaxy.
okay.
So for
So
the
it's
little-
star or something?
Yes,
Okay.
of course, we need a constant inflow of gas, so we need a post-merger starburst gas-rich system. Yeah, that's it.
How much does the mass of the binary grow during this process?
A lot, more or less 4 times in the more extreme cases.
It depends on the initial condition, right? So if you start from 1 parsec and not half a parsec, or like 3 parsecs, then they would grow even more. I mean, is this
Yes.
high power?
No, I think it won't depend on the initial condition, but depends on this anisotropy, because we are bound in our model, because my model is scale free within certain limits. You cannot put any value of the mass and any value of the semi-major axis, because I have this thermodynamics, this equation of state, and depends on density. So that value of the density, the critical density, is a physical value. So you need to keep the densities within a certain range. So you cannot put any value here to use my model. But of course, in reality, the total accretion of the black holes is going to be a function of the initial separation. Yes. But in my model, it's not.
You initially mentioned about photon radiation, LMR emission. Did you study it in
No.
So this thing happening somewhere detectable?
You're saying, can you say
Well,
that?
you don't study it. Okay.
Yes. Maybe I should have mentioned that, of course, some of the capture material can be expelled in outflows. We are not modeling that, but we compute that the change in the evolution of the semi-major axis is not affected a lot because you already captured the gas. In that process, you already transfer angular momentum to the black holes. So if you ejected all the material, the worst case scenario is that you affect the semi-major axis evolution by a third, 30%. So outflows, it's not going to be an issue in that regard. Of course, if you can blow up all the clouds, so you don't have any gas left.
So on a more technical level, how do you get the black holes to interact with the gas? So black holes are probably not as spiritual.
No, these are simple particles, just gravity and accretion.
Okay, so no like run pressure.
No.
Okay.
You basically assume that if the gas particle reaches within a certain radius, then it's immediately a part of the black hole.
Yeah.
Just has the angular momentum.
Exactly. You add the linear momentum. You're losing angular momentum in that, but it's not much, so it's not affecting my results. And
So you're not worried about spinning the black holes, that's the only issue that's happening there.
yes,
But the sync radius you're using is quite small compared to the scale of the simulation. So you're sort of the gas that gets bound, you're sort of part of the gas that gets bound to the records as well, the single records. So
yes,
there is an effect, but it's really rare.
yes. The sync radius, the accretion radius, is 1/10 of the separation. So you are resolving the Hill radius for it.
Why did you consider only circular binaries? So at these separations, the binaries would be typically very eccentric.
Yeah, just for simplicity. Yes, because I have been modeled some other systems with different eccentricity, and you go either increasing eccentricity or decreasing eccentricity. In the case of circular binaries, it's easier because you just increase. You just can go up.
But if it's an eccentric binary, then maybe the mechanism would be much more efficient because there you can change the eccentricity much more rapidly. Because in your case, the eccentricity change term was negligible. Because
Yes.
it was E squared, the original term.
Yeah, and the total eccentricity change is very small.
Yeah.
It's less than 1%.
In the other case, there will be a large eccentricity change. And so you can maybe drive the binary to the regime where, gravitational wave addition will be much more efficient because it's very eccentric.
Yeah, it could be more efficient. And also it's going to be much more efficient for an unequal mass binary. Because the transfer of angular momentum is going to be, the total angular momentum of the binary is smaller with a Q less than 1. So you will have a transfer much more efficient.